Okay, so this is a lesson about the derivative as a function. We learned in the last lesson that we have two formulas. We'll call them number 1 and number 2 for the f prime of a, which is the derivative at a point x is equal to a. Synonyms for f prime of a we learned last time are the instantaneous rate of change of f at x is equal to a, also the slope of the tangent line on f at x is equal to a, which means we're at the point a, f of a, right? So derivative, f prime, I roc, m tan, all of those mean the same thing. Let's talk about how we can create a new function from f of x, and we can call that function f prime of x. So this formula here is the first formula from up top. And for this whole lesson, when we're calculating f prime of x, we want to use the first formula and not the second one. So we can say that for any function f of x, we can find the derivative at every point and thus make another function f prime of x. Let's do that for the function x squared. So I'm just going to take it and use the limit formula, limit as h goes to 0. Now remember, if f of x is equal to x squared, then f of x plus h, we're putting x plus h into the x squared function, and we're going to get x plus h, the quantity squared. You can expand that out to get x squared plus 2hx plus h squared. So actually, let me write it this way first. So that's f of x plus h minus f of x, and it's all over h, okay? So now I'll expand it out like I did on the right there, and I'll get x squared plus 2hx plus h squared minus x squared all over h. These are going to cancel, the two x squares, and then I can factor an h out. So notice, before I do anything more, if I just look at this limit problem right here, if I put in h at this point, I'm going to get 0 over 0, right? So it becomes a limit problem, and we have to figure out how to get around the 0 over 0. We're going to do that by factoring the top and canceling the h. Once you do that, now if you put in 0 into that equation, you get out 2x. So I want you to recognize that in the last lesson, when we did f prime of a, we were always getting a number out. In this lesson, when we do f prime of x, we're getting a function out. So what is this telling us? Well, it's telling us that if you have a function f of x, which is the parabola, if you were to find the slope of the tangent line at every single x value along this parabola, then that slope of the tangent line will work out to be 2x, depending on where you are on the parabola. So I can make another function down here, which is f prime, that's equal to 2x. This function on top is f. So if I wanted to find the slope of the tangent line on the parabola at x is equal to 5, then I just have to do 2 times 5, right? So just come down to my 2x graph and read off the y value, right, which would be 10. So the slope of the tangent line on the parabola is 10, and that is equal to the y value on the 2x graph, which is the derivative graph. So we have generated a new function, and the y value on this new function is equal to the slope of the tangent line on the old function at any x value. Okay. Before I go ahead, I want to remind you guys that many of you have seen the power rule before, and so obviously if you do the power rule for x squared, you get 2x. We will be using the rules of derivatives starting in the next lesson, but for this lesson, we have to use the limit definition. We're not going to be able to do the power rule yet because the goal here is to understand what a derivative is. And so we're going to need to do this set of problems on this homework using the limit definition. So if f of x for the next one is equal to x cubed minus x, let's try to find an equation for f prime of x. Okay, so let's do the limit definition. So f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. That's going to be equal to f of x plus h means you're putting in x plus h into the equation. So that's going to end up looking like that. So it's x plus, well, I should have my limit notation. Don't forget that. Limit as h goes to 0, x plus h cubed minus x plus h. And then f of x is x cubed minus x, and it's all over h. So now this is the limit as h goes to 0. This thing, x plus h, the quantity cubed, if you went off to the side and did x plus h times x plus h times x plus h, then you would get x cubed plus 3x squared h plus 3xh squared plus h cubed. That's this piece right here. Then you get a minus x minus h, which is from this piece right here. And then you're going to get another minus x cubed plus x, and that's from this piece right here, okay? And all of that is over h. So now you want to simplify that numerator. So this cancels with this, and this goes away. And now we're left with 3x squared h plus 3xh squared plus h cubed minus h all over h. And then you can see that if you put in the arrow number right now, you'd get 0 over 0. So what we want to do is pull now the h out as a factor. And if we pull the h out as a factor, then we can cancel it. And now if you put in, oh, I dropped a little h here, right? This one, when you pull out an h, it's going to be 3xh. So now if you put in 0, then this term has a 0, so it becomes 0. This term has a 0, so that becomes 0. So what we're going to be left with is 3x squared minus 1, okay? And again, if you know the power rule, then of course we're going to get there. We're not ignorant of the power rule in AP Calc. We are just trying to teach you what the power rule means. It means that we've done a limit calculation, and so that's how the people who invented the power rule figured out the power rule, by doing limit calculations. So you have the privilege of joining the select group of people who actually know why the power rule works, right? So anyway, I'll get off my soapbox. F prime of x is equal to 3x squared minus 1. Okay, so something we want to notice is that f of x is a function, f prime of x is another function. F of x is a graph, f prime of x means the slope of that first graph at any x value. Now, the different functions f and f prime can have different domains. In this particular case, actually the domain of both of these functions, both of the functions are polynomials, so the domain is all real numbers, right? So you want to kind of keep an eye on the domains, because sometimes they're going to have different domains, and I think maybe the next example is one of those, so let's take a look. Yeah, let's take a look at this one. F of x is equal to the square root of x. Let's find f prime of x. So again, f prime of x, we're using that first definition, the limit as h goes to 0 of f of x plus h minus f of x over h, okay? So at this stage, if you put in 0, you're going to get 0 over 0. So we need to do some algebra, and the algebra that seems to be the one we would do here is rationalizing. So that's what I'm going to do, multiply the top and the bottom by the conjugate. That means the top is going to become the limit as h goes to 0 of x plus h minus x, and the bottom is going to become h times rad x plus h plus rad x. So now these x's are going to cancel, and then the h's are going to cancel, and they're going to leave a 1 behind. So now we can put in h is equal to 0 into what's left over, and you would get the answer 1 over rad x plus rad x. Rad x plus rad x is 2 rad x, okay? So f prime of x is a function which is 1 over 2 rad x. So now if you look at f of x, it's the square root function, right? So if we're just thinking about what's going on graphically, f of x is the square root function, and f prime of x is 1 over 2 rad x. You might not know exactly what that looks like, but you can see that at x is equal to 0, you're going to have an asymptote, right? So let me draw f prime in blue, and f prime is going to do something like this. It's going to look something like that, okay? So if you think of the domain of f, the domain is x greater than or equal to 0. If you think of the domain of f prime, it is x is greater than 0, because right here on the axis we have an asymptote. So what is this telling us? Well, this is telling us that actually the derivative for this function, let me draw this a little better. The derivative, for this f function rad x, right at x is equal to 0, the derivative doesn't exist. The reason is that the slope of the tangent line right at x is equal to 0 is infinite. So because of the vertical tangent line, f prime doesn't exist right at the point x is equal to 0. So places where you see that a number, like in this case 0, is in the domain of f, but it's not in the domain of f prime, those are places where we say that the function up here, this function, is not differentiable at x is equal to 0. It doesn't have a derivative there. Why? Because the derivative is the slope of the tangent line. If the slope of the tangent line is infinite, then that is not that's not a number. So we don't have a derivative at that spot. Okay, notations for the derivative. Notations for the derivative, well, this was actually a really interesting historical topic because Newton and Leibniz, these were our two people who came up with calculus, right? And Newton had a notation which is similar to the f prime notation. So he would say f prime of x or something similar to that, or y prime, right? Those mean the derivative of f. The Leibniz notation says dy dx, right? Dy dx means the derivative of y with respect to x. Sometimes we'll say df dx, where x is f is the function, or even df of x dx. All of these things mean the same thing. They mean the derivative, and we're going to be using all of these notations, so you want to be familiar with that. Okay, next we have the concept of differentiability. A function is differentiable at a point x is equal to a if f prime of a exists. A function is differentiable on an interval if it is differentiable at every point in the interval. So if you think of a function like the absolute value function, and the question says, where is that function differentiable? Well, let's draw the function. Absolute value function looks like this. And then if you were to draw its derivative, let's write the absolute value function as a piecewise function. So this is like a review of something we did in Unit 1. We could take the derivative of each of those branches, right? And the derivative of x, well, that's going to be, remember that if you just have a line, the derivative is just the slope of the line. So it's 1 for the red line, and it's -1 for the blue line. And this is x greater than 0, and this is x less than 0. So if I draw a graph of f prime, it's going to look like 1. The y value is 1 here because the y value on f prime means the slope on f, right? So we have that, and then on the other side we have this, right? So this is at 1, and this is at -1. So if I wrote the domain, right, of my f function, it would be all real numbers, but the domain on f prime would be x not equal to 0. So places which are on the domain of f but are not on the domain of f prime, those are places where we're not differentiable. So in this problem, we would say f of x is not differentiable at x is equal to 0. So we can say that here, f of x not differentiable at x is equal to 0. Graphically, that means that at x is equal to 0, we cannot draw a unique tangent line, no unique tan line, because if you think of what a tangent line means, we have to touch this point and we have to be going in the direction of the curve. Well, if you're coming in from left to right, coming towards 0, the curve is going this way, and then once you pass 0, the curve is going that way, right? So at x is equal to 0, we don't have a unique direction, and that's why there is no unique slope of the tangent line. There is no derivative. We're not differentiable. So we have a theorem which says that if f of x is differentiable at some x value, then it must be continuous there, right? Because if you can draw a tangent line and measure its slope, then the function must be actually continuous at that point. If you have a hole or something, then you can't even draw a tangent line, a unique one. If you have a jump, you can't draw a tangent line, right? So if we're differentiable, then that must mean we're continuous. But if we're continuous, like this absolute value graph is continuous at x is equal to 0, but it doesn't have a derivative there. So f of x being continuous at a value does not mean that we are differentiable at that x value. Okay. Okay, ways for a function to not be differentiable. The first way is when there's a sharp corner, and that looks just like the absolute value function. So if you have a function that looks like that, then at x is equal to a, there's a sharp corner. So we are not differentiable at x is equal to a. You could have a corner that looks a little different, but it's still a sharp corner like that, right? So that would also be not differentiable at x is equal to a. There's something called a cusp, which looks kind of like this, right? Which is still a sharp corner, and that is also not differentiable at x is equal to a. So all of these are not differentiable at wherever that sharp corner happens. If you are not continuous, if you have a discontinuity at x is equal to a, then that's another way in which you can fail to be differentiable, because if I make a graph that looks like that, or even if one of these is filled in, there's no way to draw a unique tangent line here at the jump x value, right? So we're not differentiable at that x value. You could have a hole or something that would also be not differentiable. So I guess I should say a discontinuity, right, is going to be not differentiable at that x value. So this function, right, everywhere else, like all along here and on the other side of the hole, we're fine. It's just at the hole, we're not differentiable. Okay, and then the last way is when there's a vertical tangent line. So a graph like, for example, x to the 1/3. That's a good example of a graph that looks kind of like this, and then it comes in like that. It's like the x cubed graph on its side, but right as it goes through 0, right there is what we call a vertical tangent line, which means it's a tangent line which will actually cross the graph. It'll look like, if you kind of zoomed into that, let me draw that better. It's gonna do something like it actually crosses the graph right there, and its slope is infinite. So when that happens, when the graph kind of goes vertical for just a one point like that, then the function is not differentiable at that spot, right? So not differentiable. The way I drew this x to the 1/3 graph, it would be not differentiable at x is equal to 0. Okay, so why do we care about differentiability? Well, if a function is differentiable somewhere, then it means that as you zoom further and further in, that function will look more and more like a line, right? And in notability, you can actually do this, if you have a graph, and you're at some point, a curve, a nice smooth curve, and you're at a point where it is differentiable, then if you keep on zooming in, you're going to see that that looks more and more like a line. So we can model it with a line equation, which is a lot simpler than a curve equation, and that's why we like it when functions are differentiable. A differentiable function at x is equal to a, we say that it is locally linear at x is equal to a. Okay, higher order derivatives, what are those? Well, higher order derivatives just means that you can keep on doing a derivative process, right? So if f of x is equal to x squared, we already found that f prime of x is equal to 2x. And f double prime simply means you take this equation and you do the derivative for that, right? So I would do f of x plus h minus f of x and all of the jazz, and I would get 2x plus 2h minus 2x over h. These would all cancel, and I would get 2, right? So the second derivative is f double prime, and in this case, f double prime is equal to 2. I can do that again and take a derivative of this second derivative, and that would give me the third derivative. So f triple prime of x. And if f double prime of x, if that function is just a constant, right, then that just means that we have a flat line at f double prime of x is just a flat line at y is equal to 2. The derivative of a line is the slope of the line, right? So the third derivative, which is the derivative of that line at 2, is just going to be 0, right? And, you know, in this particular problem, all the higher derivatives than that would be 0. But the point we're taking away is that we can go on doing the derivative process and we get these higher order derivatives. If you go past triple prime, then we don't write it with so many tick marks. We have this notation which is f and then a little 4 in the exponent with the parentheses, right? This would be the fourth derivative. Now that's important to have those parentheses there, because without the parentheses, if I write f4 of x, that means I'm taking f of x, right, and raising it to the fourth power. So we want the parentheses for the fourth derivative, and then so on. If you're doing the 100th derivative, then f parentheses 100 x, that means the 100th derivative. With the d dx notation, you know, dy dx is the first derivative, then d squared y dx squared. It's said in a little bit different way. D squared y dx squared, that's the same as f double prime, second derivative. D cubed y dx cubed is the third derivative. And then d, we just put a number like that, d4y dx to the fourth, this is the fourth derivative, and so on. Actually, I should say f4 parentheses. Okay, so those are our notations. I actually put that there, but we're done with this slide. And the last thing, oh, takeaways. So we're done with the lesson. So please pause the video, do the takeaways, and then check them. Have a great rest of your day, and we'll see you for D3.